Today we will start with IR spectroscopy. We have already done UV spectroscopy and now we will be doing IR spectroscopy, that is infrared spectroscopy. In this, first is, as we have already done the electromagnetic spectrum, the IR comes between the visible and microwave region. This we have also seen in the diagram, that is in the electromagnetic spectrum, and it measures mainly it measures the bond vibration frequencies. This is important. IR measures the bond vibration frequencies in a molecule and is used to determine the functional group. So we have already seen in an electromagnetic spectrum that this is the electromagnetic spectrum. In this, the frequency and energy are shown. In this, here is the frequency, high frequency, and here it decreases, and so the energy decreases as energy and frequency are directly proportional, and the wavelength is inversely proportional, so wavelength decreases in opposite direction. So in this we have done UV spectroscopy already. Now we will be doing IR, and IR lies between the UV visible region and microwave region. So it is in between the UV and microwave region, and this involves the bond vibrational frequency. Now UV and microwave, in between is IR, and it is vibrational IR. So IR ranges 2.5 micron to 15 microns. Now this we have already seen. So now the spectrum and molecular effects, this we have seen in the previous, that this is the visible region, that is the UV region, UV vacuum region, then UV near UV region, then visible region. These three together we have done in UV. So, and these three mainly involves the electronic transitions, and this we have seen there are 4 types of electronic transitions. Out of these, mainly we were concerned with 2 electronic vibrations, that is pi to pi star and to pi star transitions. Now in this IR region we are concerned with bond vibration frequencies, that is molecular vibrations, and in this IR requires less energy than the UV. So if we study IR, in this we will be seeing that first rotational frequencies occurs, then the vibrational, and then the electronic, as the energy is provided to the molecules. So we have seen in UV, or that is visible range, electronic transitions, and in this IR we will be dealing with vibrational frequencies of a bond. And in X-rays generally bond breaking takes place, and therefore in the X-ray areas always the technicians take care of this, because bond breaking takes place, that is they are high energy radiations. And in the microwave, which we use in our microwaves, there are rotational of molecules takes place, and then in radio frequencies, which we will be dealing after this chapter, that is in which we will be doing NMR, deals with radio frequencies. So in this IR we will be doing vibrational frequencies of the molecules. In so infrared region, that is IR, in which we have done in electromagnetic spectrum, that is the range is from, it extends from 0.8 micrometer to 1000 micrometer, and is divided into 3 main parts. that is, as we have seen in UV region. Now it is also divided in three parts: near IR region between 0.8 to 2.5, and middle infrared region, that is 2.5 to 15. This region is mainly important. We will be doing mainly about this region, and then far infrared is 15 to 200 micrometer. So we are concerned with mainly that is middle IR region, which is between 2.5 to 15. And so in this, if we calculate, so this region is provides the greatest information, that is middle region provides the greatest information for the elucidation of molecular structure, and most IR spectrophotometers are limited to the measurement in this region only. And so we are concerned with the main middle region only. And in this, now it prefers to describe this region in terms of wave numbers. Generally, different spectroscopies take different units. In IR spectroscopy, we mainly deal with the wave numbers in terms of wave numbers, that is centimeter inverse. And we know that nu is equal to 1 over lambda, and lambda is in centimeters. So in this region, we corresponds to, we have done, the region is from 2.5 to 15. So in terms of wave number, it comes out to be 1 over 2.5 into 10 to the power minus 4 centimeter, that is, it comes out to be nearly 4000 centimeter inverse. And when it is 15 then micrometer, then it comes out to be 667 centimeter inverse. So we deal with the area, that is middle region, that is from 2.5 to 15, or that is in terms of centimeter inverse, in terms of wave number, 4000 to 667 centimeter inverse. And now energetically, this rough amounts to providing 4.8 to 48 kilojoules per mole. So the stretching or the vibration frequencies mainly are calculated by a law, that is Hooke's law. Hooke's law is used for the calculations of the stretching vibrations of the molecules. That is, the frequency of the stretching vibration of any bond can be calculated by using this law, that is Hooke's law. According to this law, wave number is equal to 1 over 2 pi c under root k over mu, where the different terms used has different meanings. So here the reduced mu is reduced. So wave number is given by 1 over 2 pi c under root k over mu, where the various terms has its own meanings. And mu is also given by, mu is equal to m1 under root m1 m2 over m1 plus m2, where m1 m2 are the masses of the atoms used, that is in which the bond is present, and mu is the reduced mass, as I have already told you earlier. And mu is the reduced mass, and nu is the frequency, nu bar is the wave number we have used here, and c is the velocity of light. So we can say that different kinds of atoms have different masses, and different kinds of bonds have different strength. So different kind of atoms have different masses, and the different kind of bonds have different strength according to the masses of the atoms. Therefore, different combination of atomic masses and bond energies give system that can vibrate at different frequencies. And when the molecules absorb electromagnetic energy at this, when it bends, different vibration motions of the atoms in the same molecule can also lead to absorption at different wave numbers. So mainly we can say that the different atoms have different masses, so different kinds of bonds have different strengths, and according to that they absorb the different frequencies. And we can explain this in detail. We can say that vibration frequency or the wave number depends upon bond strength, that is the bond present between the atoms of a molecule, and it is directly proportional to the strength of bond. Example, if we take in this triple bond, that is in alkyne, C triple bond C and C double bond C and C single bond C. In this bond is strong and it will have high frequency than the double, than the single, and these bond has frequency this at which their vibration takes place, and for this is 1650 and this 1200. So the bond strength is, the frequency depends upon the bond strength. And similarly, mass has its effects. Vibration frequency is inversely proportional to masses, as we have seen in the formula of Hooke's law. And so in this we can say the I has mass because it is in the periodic table, it is lying down. As we move down the group, the masses increases, so it has the greatest mass, then this, then this, then this, then this. Hydrogen has less mass as compared to these other atoms. So vibration frequency is inversely proportional. So this has 3000 vibration frequency and this has 500 frequency at which the atoms vibrate. And third factor is hybridization. This hybridization also affects the bond strength, or say force constant. In this we can say that bonds are stronger in the order this, that is in as the S character decreases. In this it is 50% S character, in this 33%, and it is 25%. As the bonds are stronger, this bond is stronger, so is the their frequency, and this has 3100 centimeter inverse, in this 2900 centimeter inverse. So these we already know in this sp hybridization there is a triple bond, in sp2 there is double bond, and sp3 there is a single bond. So these are the main three factors on which the bond strength depends. That is, first is the their bond strength on the frequency or wave number depends. First is the bond strength, second is the mass, and third is the hybridization. So we can easily explain how the bond strength is different for different type of molecules, different type of bonds, and then how the frequency or vibrational frequency depends on that. Then we will start with the principle of IR spectroscopy in the next lecture. Thank you.